Many of the products we use every day are produced from raw materials. Distillation is a process that's often used to turn raw materials into finished products. Because distillation is involved in the production of so many products, it's important for plant operators to understand how it works. Distillation is a process that uses heat to separate two or more substances in a liquid mixture. This is done by vaporizing one or more substances in the mixture and separately recovering the vaporized substance and the substances left over. To fully understand distillation, it's important to understand the physical principles that make the distillation process possible. The basic physical principle involved in the distillation process is changing states of matter. First, a substance in a liquid mixture is changed to a vapor. Then, to recover the separated substance, the vapor is changed back to a liquid. Matter normally exists in one of three different forms or states: as a solid, as a liquid, or as a gas or vapor. The term vapor is often used to identify a gas that's created by heating a liquid. Most substances can exist in all three states of matter. For example, we usually think of water as a liquid, but water can also exist as a solid, ice, or as a vapor, steam. All matter is composed of very small particles called molecules. These molecules are constantly in motion. The state of a substance depends on the speed at which its molecules are moving and the strength of the bonds between the molecules. One way to change the state of a substance is to apply heat to it. For example, when heat is applied to water, it speeds up molecular motion. As a result, the bonds holding the molecules to each other weaken, and the molecules are released as steam. Heat is applied during the distillation process to change a liquid substance to a vapor. Later, heat can be removed to change the vapor back to a liquid. Distillation involves changing matter from one state to another. Two of the factors that affect changes of state are heat and temperature. In this part, we're going to look at how heat and temperature affect the distillation process. Let's look at an example. When heat is applied to water, the water molecules move faster and the water's temperature increases. If we apply enough heat to raise the temperature to 212 degrees Fahrenheit, which is the boiling point of water at atmospheric pressure, bubbles of water vapor are formed. When these bubbles reach the surface of the liquid, they escape from the liquid as steam. Steam is a vapor. It's a gaseous form of water, which normally exists as a liquid. The process of turning a liquid into a vapor is called vaporization. In this illustration, we've added a dome to contain the vapors. When the temperature of a vapor is lowered, for instance by the cool air circulating around this tube, its molecules will move slower and closer together until it turns back into a liquid. When a vapor is cooled, it condenses into a liquid. This process is called condensation. Now, to raise the temperature of a substance, we apply heat. To lower the temperature of a substance, we remove heat. The heat that's associated with changes in temperature is called sensible heat. Changes in temperature can be measured by a thermometer. A thermometer can sense and measure temperature changes as sensible heat is applied or removed. The heat that's applied to water to raise its temperature to the boiling point is sensible heat. When heat is applied after the boiling point of a liquid is reached, the temperature of the liquid does not continue to increase. The heat that's applied after a liquid starts to boil is absorbed by the molecules as the substance passes from the liquid state to the vapor state. The heat associated with a change of state is called latent heat. Latent heat is observed as a change in state, not as a change in temperature. The term boiling point refers to the temperature at which a liquid boils at a given pressure. But in the context of distillation, there is more than one boiling point. That's because the liquid being distilled is a mixture of two or more liquids, each of which has a characteristic boiling point. Because each substance in a liquid mixture has its own boiling point, the mixture has a range of boiling points, which is known as the mixture's boiling range. The boiling point of the component in the mixture that boils at the lowest temperature is the mixture's initial boiling point, or IBP. The mixture's final boiling point, or FBP, is the temperature at which the component that has the highest boiling point boils. The final boiling point is also commonly referred to as the end point of the mixture. The end point is the end of the mixture's boiling range. One of the factors that affects the distillation process is pressure. One type of pressure is vapor pressure. Vapor pressure is the pressure exerted by vapor molecules that escape from the surface of a liquid. To get a better understanding of vapor pressure, let's look at an illustration of a closed container of liquid. In any liquid, some molecules escape the surface of the liquid as vapor, and some of the escaping vapor molecules return to the liquid. The escaping molecules create pressure by colliding with the container's walls. The more molecules that escape the liquid, the greater the pressure. Eventually, a point can be reached at which the number of molecules escaping from the liquid equals the number of molecules returning to the liquid. The pressure exerted by the escaping vapor molecules at this point is called the vapor pressure of the liquid. A liquid's vapor pressure indicates how rapidly the liquid will vaporize at a given temperature. For example, a low vapor pressure indicates that a liquid produces a small amount of vapor at a certain temperature. A liquid with a high vapor pressure has a low boiling point. Vaporization occurs at a low temperature, so the liquid does not require much heat to begin boiling. On the other hand, a liquid with a low vapor pressure has a high boiling point. Now, there are actually two types of pressure that are important to distillation. We just saw how vapor pressure affects the process. The other type of pressure is external pressure. External pressure is basically the pressure that a substance is exposed to. In an open container, the external pressure is the pressure exerted by the atmosphere. In a closed container, the substance is exposed to pressure inside the container. We'll use this open container of liquid to understand the relationship between vapor pressure and external pressure. With the container open, the liquid is exposed to atmospheric pressure. In order for vaporization to occur, the vapor pressure must overcome the external pressure that's acting on the surface of the liquid. One way to cause vaporization to occur is to increase the vapor pressure by heating the liquid to its boiling point. Another way is to decrease the external pressure. For example, if we close the container and draw the air out to reduce the pressure on the liquid will boil at a lower temperature. Less heat will be necessary to increase the vapor pressure enough to overcome the external pressure. On the other hand, if the external pressure is increased, the temperature required to boil the liquid will also increase. If the pressure is increased, for instance, by 100 pounds per square inch, the boiling temperature will increase. In this case, the water will not boil until its temperature reaches 338 degrees Fahrenheit. The higher temperature is necessary to give the liquid molecules sufficient energy to overcome the increased pressure on the liquid. Now, because a liquid that's being distilled is a mixture of two or more liquids, the term partial pressure is used to refer to the vapor pressure of an individual component in the mixture. The sum of the partial pressures of all the components equals the mixture's total vapor pressure. One additional term that's important to a discussion of the distillation process is relative volatility. Relative volatility is the relationship between components in a liquid mixture as determined by their boiling points. Let's look at two examples. Pentane boils at approximately 96 degrees Fahrenheit at atmospheric pressure. Suppose pentane is one of the components in a liquid mixture to be distilled. The other component is heptane, which boils at approximately 209 degrees Fahrenheit at atmospheric pressure. The boiling points of the two components are relatively far apart. This mixture has a high relative volatility. It would be fairly easy to separate the two components using distillation. Now let's examine a liquid mixture of butane and isobutane. At atmospheric pressure, butane boils at approximately 31 degrees Fahrenheit. Isobutane boils at approximately 11 degrees Fahrenheit at atmospheric pressure. This mixture has a low relative volatility. A low relative volatility means that the components are relatively hard to separate by distillation because their boiling points are close to each other. Well, we've covered a lot of information in this topic. We saw how changes in the state of matter relate to the distillation process, and we saw how temperature and pressure affect aspects of the distillation process. Now try a few practice questions to check your understanding. The basic physical principle involved in the distillation process is changing states of matter. First, a substance in a liquid mixture is changed to a vapor. Then, to recover the separated substance, the vapor is changed back to a liquid. The boiling point of the component in the mixture that boils at the lowest temperature is the mixture's initial boiling point, or IBP. The mixture's final boiling point, or FBP, is the temperature at which the component that has the highest boiling point boils. The final boiling point is also commonly referred to as the end point of the mixture. The end point is the end of the mixture's boiling range. Relative volatility is the relationship between components in a liquid mixture as determined by their boiling points. Let's look at two examples. Pentane boils at approximately 96 degrees Fahrenheit at atmospheric pressure. Suppose pentane is one of the components in a liquid mixture to be distilled. The other component is heptane, which boils at approximately 209 degrees Fahrenheit at atmospheric pressure. The boiling points of the two components are relatively far apart. This mixture has a high relative volatility. It would be fairly easy to separate the two components using distillation. Now let's examine a liquid mixture of butane and isobutane. At atmospheric pressure, butane boils at approximately 31 degrees Fahrenheit. Isobutane boils at approximately 11 degrees Fahrenheit at atmospheric pressure. This mixture has a low relative volatility. A low relative volatility means that the components are relatively hard to separate by distillation because their boiling points are close to each other. During the distillation process, a liquid mixture is separated by vaporizing one or more components of the mixture, and then the vapors are condensed. In this part, we're going to look at how a binary liquid mixture, that is, a mixture that has two components, can be separated into a lighter component and a heavier component. We've set up a laboratory demonstration to do this. In order to separate the components of a liquid mixture, a distillation system must have a container for the liquid mixture, a condenser. This one consists of an inner tube for the vapors and an outer tube with cooling water running through it, a receiver to collect the liquid leaving the condenser, and a source of heat. We'll use an electric heater. The liquid mixture we'll use consists of 50% pentane and 50% cyclohexane. These components have boiling points that are relatively far apart. At atmospheric pressure, the boiling point of pentane is approximately 96 degrees Fahrenheit, and the boiling point of cyclohexane is approximately 177 degrees Fahrenheit. In this example, the pentane is the lighter component. Its boiling point is lower than that of cyclohexane. The cyclohexane is the heavier component, and it has a higher boiling point. As temperature increases and the mixture's initial boiling point is reached, the lighter component starts to boil and vaporize. But because the heavier component has some vapor pressure at this temperature, some of it also vaporizes. The vapors condense in the condenser, and liquid starts to collect in the receiver. When the distillation process is complete, we can analyze the contents of both the receiver and the container. The mixture in the receiver is primarily pentane, but there is some cyclohexane. The mixture in the container, on the other hand, is mostly cyclohexane, with a small amount of pentane. During the process, a large part of the lighter component vaporized, while a small part of the heavier component also vaporized. If we were to repeat the process and distill the liquid in the receiver, we would get a higher concentration of the lighter product and a lower concentration of the heavier product. In this part, we'll look at batch distillation processes. A batch process is designed to distill a fixed amount of liquid. After a certain amount of mixture has been separated and its components have been removed from the system, another batch of mixture is loaded into the system and separated. There are two types of batch process systems, a single batch system and a successive batch system. Let's look at an illustration of a simplified single batch system. This system consists of a container called a still, which holds the liquid mixture, a condenser which has cooling water pumped through it, a heat source to boil the liquid mixture, and a receiver which will hold the condensed vapor. In this example, we'll use a liquid mixture of 50% water and 50% methanol. When the mixture is heated, it begins to boil. The vapors produced by the boiling liquid leave the still through a tube and enter the condenser. As the vapors flow through the condenser, they're cooled and turned back into liquid. The liquid then flows into the receiver. The vapor that's collected and condensed is called the overhead product. In this example, the overhead product contains approximately 80% of the lighter, low boiling point substance, methanol, and 20% of the heavier substance, water. The liquid that's left behind is called the bottoms product. The bottoms product in this example contains approximately 80% of the heavier, high boiling point substance, water, and 20% of the lighter substance, methanol. So you can see that a single batch system does not produce a pure separation. In other words, the overhead product contains some of the heavier component, and the bottoms product contains some of the lighter component. This can be referred to as overlap. To reduce the amount of overlap, the process can be repeated. For example, this is a successive batch system. This system has 2 stills, 2 condensers, and 1 receiver. The condensed vapors from the first still flow into the second still. The liquid in the second still is then heated until it boils. The overhead product from the second still contains more of the lighter component and less of the heavier component than the original overhead product did. By repeating the process, successive batch distillation produces a purer overhead product than single batch distillation. If a third still were added, an even purer overhead product could be produced. In this part, we're going to look at a continuous distillation process. A continuous distillation process is designed to distill a mixture that's fed to the system continuously and to produce products with a minimum amount of overlap. The products are removed continuously as more of the original mixture is fed to the system. Let's look at an illustration to see how it's done. This continuous distillation process system has 3 containers or stills, 1 heat source to boil the liquid mixture, 1 condenser, and 1 receiver to collect the condensed vapor. A feed line continuously supplies the system with a liquid mixture. During operation, heat is applied to the first still to boil the mixture. The vapors produced in this still rise and move into the second still. Because the liquid in the second still is cooler than the entering vapors, the heavier component of the vapors condenses. At the same time, heat from the incoming vapors transfers into the liquid in the second still, causing the lighter component of the liquid to vaporize. These vapors then move on to the third still, while some of the condensed liquid flows back to the first still. The same thing happens in the third still. The heavier component of the incoming vapors condenses. The lighter component of the liquid vaporizes, and some of the condensed liquid flows back to the second still. As the process continues, more and more of the lighter component moves toward the last still. From there, the vapors rise and move to the condenser, where they're condensed to form the overhead product. At the same time, more and more of the heavier component of the mixture condenses and flows back to the first still, where it's drawn off as the bottoms product. That's basically how a continuous distillation process works. Now remember, we're looking at a simplified illustration of a laboratory system. The actual equipment in your plant will be quite different. In this topic, we looked at the distillation process. We saw a demonstration and illustrations of a simple distillation process. We also looked at examples of 2 types of distillation process systems, batch and continuous. Now try some practice questions to check what you've learned. In this example, the pentane is the lighter component. Its boiling point is lower than that of cyclohexane. The cyclohexane is the heavier component, and it has a higher boiling point. As temperature increases and the mixture's initial boiling point is reached, the lighter component starts to boil and vaporize. But because the heavier component has some vapor pressure at this temperature, some of it also vaporizes. The vapors condense in the condenser, and liquid starts to collect in the receiver. When the distillation process is complete, we can analyze the contents of both the receiver and the container. The mixture in the receiver is primarily pentane, but there is some cyclohexane. The mixture in the container, on the other hand, is mostly cyclohexane, with a small amount of pentane. During the process, a large part of the lighter component vaporized, while a small part of the heavier component also vaporized. This is a successive batch system. This system has 2 stills, 2 condensers, and 1 receiver. The condensed vapors from the first still flow into the second still. This continuous distillation process system has 3 containers or stills, one heat source to boil the liquid mixture, one condenser, and one receiver to collect the condensed vapor. A feed line continuously supplies the system with a liquid mixture.